everyone, and welcome to lesson 4 of the Higher Chemistry Bonding series. We are going to have a look at intermolecular bonding today, something that's completely brand new in terms of learning the names for this type of kind of intermolecular forces, but you have seen a little bit of it at National 5 level. So, we are going to investigate the 3 types of intermolecular forces today that you have to know at a higher level. And our success criteria is to state the 3 types of intermolecular forces and how they arise. So what are they and how do they come about? So intermolecular bonding or intermolecular forces refers to the forces of attraction that are between the molecules. Now, I don't know if this will help anybody else, but it helps me. Intermolecular and between, there are lots of E's. So that's how I remember that intermolecular is forces arising between the molecules, whereas intramolecular bonding is inside the molecule, so between the atoms within a molecule. You do have to be aware of the differences between those two. So intermolecular bonding is bonding between the molecules. There are 3 types. Number 1, we have London dispersion forces. These are the weakest type of intermolecular forces. Number 2, we have permanent dipole to permanent dipole interactions. They are a little bit stronger than London dispersion forces. And hydrogen bonding, lastly, is the strongest of the intermolecular forces. So they are listed here in increasing strength, and they are in your booklet as well. So, London dispersion forces, first of all, this is the weakest type of intermolecular force. Now, these forces exist between absolutely everything. All atoms, all molecules, there is always going to be London dispersion forces. Why? Because anything which contains electrons can contain London dispersion forces because of how these forces come about. So electrons, as we know in the atom, are whizzing around in the shells. They are not stationary. They're not just staying still as we normally draw them on our target diagrams. They're actually whizzing around. I like to think of it as a little handheld fan or a ceiling fan. The electrons are moving around so much you can't see them at all. If you were to pause time, everybody who's watching this is probably going to be too young to remember Bernard's watch, but if you remember that, this watch enables you to pause time, then look at an electron's location. There are times where the electrons are found more on one side of the atom than the other. So in this diagram here, sometimes the electrons are perfectly spaced out, moving around at their kind of distance from each other, but sometimes all of the electrons can be found, for example, on the right-hand side of an atom, if we're looking at it like the diagram. What would this mean? Well, this actually changes the atom quite considerably. It's no longer electrically neutral. It has what we call a temporary dipole. So on the right-hand side, if we're talking about where we were before, all of the electrons give us a partially negative charge here. So it basically creates a dipole in the atom, but it only lasts for milliseconds. So we call it a temporary dipole. So this temporary dipole, what that does is it has one end of the atom being partially negatively charged and the other end of the atom being partially positively charged. The side with the electrons is going to be the negative side, and the side without the electrons is going to be the positive side. So, how does this actually make a force between the atoms? Well, as we know, opposite charges attract. So if you have a temporary dipole created in one of the atoms, what that's going to do is it's going to induce a dipole in a neighbouring atom. So if there's another atom here, it's then going to its negative side is going to be attracted to the positive side of the other atom, and that is going to create a force of attraction between the two atoms. Now, that force of attraction is the London dispersion force. And as I said before, it's the weakest type of attraction. These only last for milliseconds, so these are extremely easy to break. Noble gases would be your kind of go-to example for London dispersion forces. So we usually say that noble gases are inert, so they're unreactive and they don't form chemical bonds. That's absolutely true. However, if you cool the noble gases down to temperatures below minus 250 degrees, the noble gases will form solids. If atoms are going to be held together in a solid, then that must mean that they're held together by something, even though it's extremely, extremely weak. So those are the London dispersion forces. They exist between absolutely everything, all atoms, all molecules. So here are some examples. Obviously, the noble gases are non-polar because they don't have any dipoles in them. They don't bond with anything else. They don't have different electronegativities, anything like that. But for other elements, so we have phosphorus here and sulfur. Both are non-polar. Again, they are bonded with the same atoms, so they don't have any difference in electronegativity. So overall, the molecules are non-polar. However, there are differing strengths of London dispersion forces, and it is to do with the number of electrons in the molecule. So phosphorus molecules are P4 molecules, sulfur molecules are S8 molecules. Just from looking at the number of atoms within these molecules, we know that the sulfur molecules are much larger than the phosphorus ones. Now, they are going to have many more electrons than the phosphorus atoms do. So the general rule of thumb is if you increase the size of a molecule, you are increasing the number of electrons in that molecule, and therefore the London dispersion forces are going to be stronger. If you have more electrons at one side of the atom than another, then that's going to form a larger pull or a larger force of attraction. It works that way. Now, you have kind of seen this before in National 5, although you just weren't told, you didn't have to know what it was called. In Unit 2, when we did hydrocarbons, we told you that if you move up from methane, ethane, propane, butane, that the boiling points increase. And why was that? That was because as each of the molecules get bigger, the intermolecular forces of attraction are larger or stronger. And this is the reason why. It's because the London dispersion forces are stronger in molecules or atoms with greater numbers of electrons. So that's why as you increase in size, increase boiling point, because the London dispersion forces are getting stronger. Now, on to the second type of intermolecular bonding, we have permanent dipole to permanent dipole interactions. Now, just as the name suggests, we have permanent dipoles which arise in polar molecules. So we have one end of the molecule being negatively charged and the other end of the molecule being positively charged. That is a permanent thing. It's always going to be there. It's not like the electrons that are kind of coming and going. That is always there. That's why we say it's permanent. And as we know, that's due to the differences in electronegativity. Now, what happens, I hope this diagram is clear, we have a negative side of the molecule and positive side of the molecule. What that will do then, again, is be attracted to the opposite charge of a neighbouring molecule. So the iodine here, which is positively charged, is going to attract the negative end of this molecule here, which is the fluorine, and so on, and that will just continue throughout the whole substance. That is your permanent dipole to permanent dipole interaction, that bit there. So these if you were looking for a definition of permanent dipole interactions or attractions, whatever you want to call them, they are the intermolecular force of attraction between the oppositely charged ends of polar molecules. So we already know lots and lots about polar molecules. We worked through lots of stuff last week on that. So now it's just kind of incorporating the intermolecular side of things. If you have something that's permanently charged at both ends, then something else similar will be attracted to the positive or negative side of that molecule. These forces, so your permanent dipole interactions, are in addition to London dispersion forces. So even though they have permanent dipole attractions in the substance, they also have London dispersion forces, because remember, anything that has electrons, which is everything, has London dispersion forces. But so that we don't get confused, a lot of the times the SQA will only ask which is the strongest type of intermolecular force or bonding within this sample here. And that means you can just kind of ignore the London dispersion forces if it's got permanent dipole interactions. Those would be the strongest out of the two. So here is an example. This one is in your notes here. It's much kind of clearer to see. This is fluorine iodide. The fluorine is more electronegative than iodine, so it has a little delta negative there, showing that it contains a larger attraction for bonding electrons. And the iodine has a delta positive. Now, the delta positive on one iodine is going to be attracted to the delta negative on the neighbouring molecule's fluorine, and that is what holds them together. Now, that is a much stronger force than the London dispersion forces we were talking about before. So that means that something like fluorine iodide is going to have a larger boiling point or melting point and boiling point than some of the non-polar compounds that we looked at, like neon, for example, because it only has London dispersion forces. So the third type and the last type, so the strongest type of intermolecular force, is hydrogen bonding. Hydrogen bonding is something that contains highly polar bonds. So we're not just talking about like a small difference in electronegativity, we're talking a big difference in electronegativity. So what we say is it's between hydrogen and 3 other elements. And these elements are NOF elements, as I like to call them, which just simply means it's hydrogen bonded to nitrogen, or hydrogen bonded to oxygen, or hydrogen bonded to fluorine. And those are the only combinations where you find hydrogen bonding. So it's easy enough just to remember that by remembering NOF. So these are essentially permanent dipole to permanent dipole interactions. They work in exactly the same way, but they are given a different name so that we can remember that these are, 1, involving hydrogen and NOF elements, and 2, these are much stronger than just permanent dipole interactions. Why? Because there's such a large difference in electronegativity between the elements. Let's have a wee look at an example. So here is ethanol. Now, ethanol, obviously the part of this molecule which contains the carbons and hydrogens is non-polar, but we have this polar part at the end with our O and our H. The difference in electronegativity between oxygen and hydrogen means oxygen is the most electronegative element, it has a delta negative, and hydrogen has the delta positive. Now, if you have a few of these molecules together, then that means that the delta positive on this hydrogen is going to be attracted to the delta negative on this oxygen, and that is what creates a hydrogen bond. So this red dotted line here is your hydrogen bond between your ethanol molecules. Much, much stronger than permanent dipole interactions, but we will really have a look at physical properties as well as lots of things, solubility, miscibility, next time. We're just doing the very basics of intermolecular bonding right now, and we just have to know that hydrogen is the strongest, and it's between hydrogen and NOF elements. So What we wanted to achieve by the end of this lesson were to state the 3 types of intermolecular forces and how they arise. So that means, what are the 3 called, and can you draw me an example of each of these? Can you state their order of strength? And just tell me a little bit about each of the 3 types of intermolecular forces. So what we are going to do, just like every other video, we have some questions here which are on page 9 of your booklet. So if you go to page 9 of your booklet, you'll find these questions, 4 little questions to do, which will test our knowledge of intermolecular forces. So we have for 7, remember and pause the video here, go and carry out the questions and then come back and check your answers. And remember to upload a wee picture of your answers that you have marked by yourself. So 7, we have 4 different molecules and we have to state the strongest intermolecular force present in these compounds. So let's have a look at methane first. Methane is non-polar, so it only has carbons and hydrogens. There is very little electronegativity difference. Overall, the molecule is non-polar. Non-polar molecules can't have permanent dipoles because they don't have dipoles. So the strongest force in methane molecule is going to be London dispersion forces. The second one then is ammonia. Now ammonia NH3 is a polar molecule as we know, but if we have a couple of ammonia molecules together, we're going to have hydrogen bonding because we have delta positive on an H and delta negative on an N of a neighbouring molecule. So you're going to have a hydrogen bond between the nitrogen of one ammonia molecule and the hydrogen of another. Hydrogen bonding is the strongest of the 3 types of intermolecular forces, so that is obviously the strongest. C, we have hydrogen chloride, which is a polar molecule due to the difference in electronegativity, but there are no hydrogen bonding elements present here. So the strongest type of intermolecular force you can get in this example is going to be permanent dipole to permanent dipole interactions, where you have the partially negatively charged chlorine is going to be attracted to the partially positively charged hydrogen of a neighbouring molecule. And last one, trichloromethane, again, polar molecule. It's got a partially positively charged carbon and negatively charged chlorines. There is no hydrogen bonding elements. So if there's no hydrogen bonding elements and we have a polar molecule, then the strongest force is going to be permanent dipole interactions. Now for C and D, these are not the only type of interactions in or between the molecules. We also have London dispersion forces as well, but that's why the question always asks us for the strongest type so that we can highlight that it's going to be permanent dipole. If you were answering an open-ended question though, for example, it would be good to mention that you know that in addition to permanent dipole interactions, there is also some London dispersion forces as well. So question 8 was asking us, draw a hydrogen bond between the molecules of water. So we draw 2 molecules of water and put in our little polarities. So we know that the oxygen is very electronegative, so we have a wee delta negative, and the hydrogens have delta positives. Now between the delta positive hydrogen of one molecule and the delta negative oxygen of the other, this is where our hydrogen bond lies. It's one of the NOF elements, so we can definitely say it is a hydrogen bond. Question 9, which of the following molecules will have the strongest intermolecular force? So A and B, we have hydrogen iodide and hydrogen bromide. These are polar molecules, so they have differences in electronegativity, and therefore the strongest type of intermolecular force from A and B is going to be permanent dipole interactions. Hydrogen to nitrogen, as we know, is an extremely polar bond, so we'll see hydrogen bonding if this was in a molecule like ammonia, for example. Hydrogen bonding is much stronger than permanent dipole interactions. So C the H and N in a molecule of, for example, ammonia is going to be the strongest intermolecular force. Hydrogen bonding is stronger than permanent dipole to permanent dipole interactions. 10. Which of the following elements will have the strongest LDF? So we have iodine, sulfur, and argon. Now what I did here was just drew them out to see what they looked like. So iodine, remember, is a diatomic molecule. It has 2 atoms in each molecule. Sulfur is S8. It has 8 atoms in a molecule. And argon is just by itself, it's monatomic. It has 1 atom in a molecule. Now, as we know, as we have previously discussed, the bigger the molecule, the more electrons, the greater the London dispersion forces. So if we're looking at these 3, the largest molecule is the sulfur. The sulfur molecule has 8 atoms in it. It's going to have much more electrons than the other 2, and that means it will have the strongest London dispersion forces between its molecules. If we wanted to put these in some kind of order, then we could absolutely do so. And it would be the largest molecule to the smallest. So sulfur is going to be our largest. It's going to have our strongest London dispersion forces. Iodine's going to be in the middle, and argon's going to have the weakest London dispersion forces. Now, if you looked up the boiling point for 3 of these elements, then that would concur with what we have found out. Sulfur would have the highest boiling point, then iodine, and then argon. And that's what we're going to have a look at in the next lesson. We are going to have a look at how these intermolecular forces affect the physical properties of compounds. Thank you very much for watching all of the videos so far. This is going to be the last one before the summer holidays, you will be glad to know. So what we'll do is we will pick back up, do some revision of all of the bonding that we've learned so far, and then incorporate some of the physical properties. Hopefully we might be able to do some kind of experimentation. I'm not sure if that'll be physical or theoretical, but from Mrs. Calder and I, big well done and thank you for all of your hard work so far, and I hope you have a fantastic summer holiday when it comes.